When a baseball arcs through the sky, its journey is entirely predictable. It doesn't wander off or explore different routes. It takes one specific, unwavering path from the moment it leaves a hand until it hits the ground. Nature is obsessed with efficiency. It forces objects to take the shortest, easiest path possible, a rule known as the principle of least action. Because there is only one path to track, the math needed to calculate where that ball will land is simple enough for a high school student. In our everyday world, reality makes sense because everything we see commits to a single, calculable destiny. But that logic falls apart when we look at a single photon, a tiny particle of light, and fire it at a wall with two small slits. If it acted like a baseball, you'd expect it to fly through one hole or the other, forming two straight lines. Instead, they create a complex pattern of stripes, behaving like ripples in a pond, passing through both slits at once and interfering with themselves. To explain this, physicists like Richard Feynman were forced into a mathematical corner. Since they couldn't see the path, they had to assume the particle took every possible path at once, billions of zigzags and loops, all to calculate where one stripe might land. This left physics with two incompatible realities: the simple, logical world we live in, and a subatomic world that required infinite calculations just to understand a single particle. Researchers at MIT believed there was a way to bridge this gap and find a simpler route to the same answer. They wondered, what if we use the simple rules of the macro world, but allow the math to look at more than one path at a time? To see how they did it, think about water spraying from the powerful nozzle of a garden hose. Most of the water goes straight, but a light mist spreads out toward the sides. That spread shows you the likelihood of where a droplet will land. The thicker the mist in one spot, the higher the chance you'll find a drop there. By combining that spread with the classical rule of taking the easiest path, they created a way to map out quantum behavior without needing to track an infinite number of routes. When they applied this to the double-slit experiment, they only had to calculate two straightforward paths that spread out like mist from a hose. Right where the two sprays overlap, they create the exact same striped pattern that previously required billions of calculations to predict. This new approach arrives at the exact same results as the Schrödinger equation, the gold standard of quantum mechanics, using much simpler tools. The team replaced a mathematical nightmare of infinite zigzags with a single, unified method that works for objects of any size. This gives us a clear, intuitive map for a part of our universe that has always been difficult to navigate. The biggest hurdle in developing subatomic technology has been the sheer amount of computing power required to predict how these tiny particles will move. By making the complex math easier to calculate, we can design the next generation of quantum computers more efficiently. It also helps scientists simulate molecules faster, which can drastically reduce the time it takes to discover new life-saving drugs and innovative materials. We are learning that the subatomic world isn't an impossible mystery. Sometimes the most complex secrets of the cosmos are as easy to understand as watering your lawn.